This is the second lecture in Unit 2. It's entitled What's the Hurry? It says, Nature does not hurry, yet everything is accomplished by Lao Tzu. So, the learning goals for this is that you be able to determine the acceleration from a velocity versus time graph, that you be able to determine the change in position from a velocity versus time graph, and determine an unknown using this equation that's on the formula chart. So, what we already know. We know that objects can change speed or velocity if you look at it based on the lab that we did. We know that an object can speed up if you press a gas pedal in a car, the car will get faster. If you step on the brake, the car will get slower. So those are things we already know from middle school. Now what we learned in this specific lab is that the longer the ball was allowed to roll along a ramp, the larger its final velocity was. So the ball accelerates, or it allows the velocity to increase, and that the larger the angle, the greater the acceleration. So measuring velocity. We've done this in several labs already, but whenever we measure velocity, velocity is determined by, in a photogate situation, taking the diameter of the object that passes through the photogate and dividing it by the time of that particular photogate. And what that allows you to do is it allows you to measure two different velocities. Here you have the initial velocity and the final velocity depending on which of the photogates you use. So velocity can also be measured directly with a radar or a LiDAR. Once again, it's not really directly, it's using something just a little bit different. But velocity can also be measured indirectly, and that's using the Doppler effect, which we'll look at when we talk about waves. Now, there's also acceleration. Acceleration that we talked about in this lab is defined as the rate of change in velocity, magnitude, or direction. Acceleration is a vector. It requires both magnitude and direction, just like velocity. It requires both magnitude and direction. And the international standard unit for acceleration is the meter per second squared. Now, the reason why you see this character, I don't know if you remember this guy from Despicable Me. His name is Vector. Okay, and so acceleration is a vector as well. So examples of acceleration. When you step on the gas, okay, if you're in a car, you step on the gas, you're actually increasing your speed or your velocity if you want to look at it that way. So that's an example of an acceleration. Now, another example is when you step on the brake. When you step on the brake, you generally don't think of that as being acceleration. Usually we call it deceleration. But really what that is just a negative form of acceleration. So anytime you see the word decelerate, really what that means is a negative acceleration value. So it ends up being like -5 meters per second squared. Now, another thing that's an example of an acceleration, even though you may not think of it as being that, is turning the wheel. Okay, whenever you turn the wheel, you're changing the direction of the car. Whenever you change the direction of the car, changing direction is changing velocity, and by definition, a change in velocity is a change in acceleration. So a car, if it maintains 20 miles per hour, can still accelerate if it's changing its direction. And that's kind of confusing for some people. So go ahead and make sure you can take a look at that. So whenever we're comparing velocity and acceleration, the reason we want to do this is that for some reason these terms tend to be very confusing for people, that they're very, very, very different. So this is a term of how fast. So how fast is velocity? Okay, whereas acceleration is rate of change in speed. Okay, so it's one of those things where a sports car that can go up to 200 miles per hour has a high velocity, but a sports car that can go from 0 to 60 in 2 seconds has a high rate of acceleration. So they're different things. Velocity is measured in meters per second. Acceleration is measured in meters per second squared. They do have some things that are in common, so that may account for some of the reasons why we get them confused. They're both vectors. Okay, they both have magnitude and direction. They both are rates. In other words, they depend on time. Velocity is the rate of change in position. Acceleration is the rate of change in velocity. Okay, they can both be negative or positive. Okay, so there are some similarities, but there are some fundamental differences. They fundamentally measure different things. Velocity is generally measured with radar, although it can be done with the photogate, a single photogate. And if you're trying to measure acceleration, you generally need two photogates, or there's something called an accelerometer. Now, from the investigation, we actually plotted a function of time versus velocity. And when we did this, we found that the acceleration was the slope of a velocity versus time graph. And that makes sense. Now, if you look at the slope, okay, you have velocity. Whenever you're talking about finding the slope, that's change in y over change in x. Well, change in y in this case is velocity, so that's the same thing as saying change in v. And then here we have t, change in t. This is the rate of change in velocity, which is the definition of acceleration. Now, something that some people didn't quite get off the top was the fact that position can also be found from a velocity versus time graph. And it's not just taking the velocity and multiplying it. Instead, you're trying to find the average velocity. So in this example, it says, I want to know what it is in 10 seconds. Well, whenever you're trying to find the displacement of a car in 10 seconds, you actually have to find the area under the curve. The area under this curve is represented by the triangle. And if you think about it, this actually represents the average displacement if we use an average velocity. Okay, since this is a triangle, the formula is for a triangle is 1/2 base times height. Now, if you were to look at this from the perspective of, let's just look at the 1/2 height. You have a height here, and you have a height of 0. So the change in these two things right here, multiplied by 2, or adding them up, multiplying by 2, actually ends up being the average velocity. And when you take the average velocity and multiply it by the time, you end up getting this. I'm just trying to show you the origin of the displacement, but just know this: if you have a velocity versus time graph, the slope is the acceleration, the area is the displacement. So if we look at an example, it says, what is the initial velocity of a car shown to the right? So the key word is the initial velocity, and if you look at the initial velocity, it's the first velocity that's shown, or the velocity when t is equal to 0. So we come right here, we look at it, we read that particular point, and when we look at that point, we would say that it's 5 meters per second. The next one, it says, what is the acceleration of the car shown to the right? So whenever we're looking at acceleration, we say acceleration is the slope. Now, since this is a straight line, you can actually choose any 2 points on the graph. Generally speaking, you want to pick points in which you don't have to estimate if you can. For example, this point is clearly 0, 5. It's on the line for both terms. This point right here is clearly 5, 20. Now, I could choose any other points in between, but if I make a mistake in estimating, it may throw off the value of my slope. So I can actually choose any points. If I wanted to choose the first 2 points and I was comfortable with my estimate, I could do that as well. So now I need to find the slope. Remember, slope is the change in y over the change in x. So here's my y value and my y value. The change is the final minus the initial, or 20 minus 5, divided by 5 minus 0. Whenever you do this, you end up getting 15 over 5, or a slope of 3 meters per second squared. The master example says a car starts at a position of minus 20 and moves according to the graph shown to the right. What is the final position of the car? So you're trying to find the final position of the car, so you look at the last time, and that's kind of our cutoff right there. And what I need to do is I need to find the area of this particular object. So in order to find the area of this particular object, it's going to be kind of difficult because it's clearly not a triangle. But what I can do is I can divide it into 2 known shapes. I have the shape of a triangle, and then I have the shape of a rectangle right here. And if you can take those 2 shapes, find the area of each, and then add them together, that'll be the total area under the curve. So I have an object that starts at minus 20. Now I have to add the displacement in order to figure out what the final position is going to be. So let's find the area under this particular curve. I'm going to start with a rectangle. The rectangle has a side of 5 and a side of 5. Okay, if you take those things, you multiply them out, you end up with an area of 25 just from the rectangle. But now you have to add the area of the triangle. If you were to look at the area of the triangle, it goes up to 20, but remember, that's no longer part of the whole 20 is no longer part of the triangle. Instead, only 15 is the height of the triangle, because remember the other 5 was the rectangle. So the triangle has a height of 15, and it still has a base of 5. So you would do 1/2 base times height. And whenever you do this, okay, you go ahead and put it in your calculator, 0.5 times 5 times 15, and it gives you a value of 37.5, which you then have to add to the original 25. So that means our total displacement is 62.5 meters. But remember, that's our displacement. If we start at minus 20 and we move a positive 62.5, then we have to go ahead and say, let's add this in. If we add that in, we end up with the final position of 42.5 meters. Measuring acceleration. So, if we're looking at acceleration, we need to know, in the lab, we had to figure out, okay, what's the diameter of the first marble divided by the time minus the diameter of the second marble divided by the time divided by the overall time. This is the formula that was given to you in the lab, and what that correlates to is this particular formula right here. The final velocity is this term, the initial velocity is this term, and the time between the gates is the change in time that goes right there. So this is the more broad version of this particular formula if you're using something that's not a photo gate, if you're using a car, for example. So now, measuring acceleration. Generally, we measure acceleration with a device that's called an accelerometer. There are accelerometers in Wiimotes, PlayStation 3 controllers, PlayStation 4 controllers, Xbox controllers, iPhones, iPods, digital cameras. All those things have accelerometers in them, and you can tell them because they can detect how quickly the motion changes. There was a game that was pretty popular a couple of years ago in which you threw a punch with your phone in a fist, and it would actually tell you what force you punched with. And there was a way to cheat. If you just kind of snapped it back and forth, it actually worked a lot better than if you actually did the actual punch. So you come up with this accelerated motion equation. You should be familiar with these variables, but let's go through them. The first one is we have acceleration. The variable is a for acceleration, and the definition is it's the rate of change in velocity. So it's the change in velocity over time. Okay, you need to put that into words, but it's the rate of change in velocity. The SI unit is the meter per second squared, and it's measured with an accelerometer, which is what we just referenced. The other variables you should be familiar with from the first presentation. You have final velocity, you have initial velocity, and you have time. Now, if you can't remember what the names and the definitions and the units and so forth are, you should refer to your notes from the first presentation because this is something you're expected to know moving forward. Developing B1, it says a car accelerates from 6 meters per second to 15 meters per second in 3 seconds. Determine the acceleration of the car. So like always, I'm going to go ahead and underline the numbers, and I'm going to circle what I'm trying to know, and I'm going to write them out. Okay, so I have a velocity and a velocity. So I have two velocities of 6 and 15. Now I need to decide which one is initial and which one is final, and it says from 6 to 15. So that lets me know 6 is initial, 15 is final. The time is 3 seconds. So I'm trying to figure out what the acceleration is, and I'll use the equation A equals Vf minus Vi over t. I plug in my numbers and I get 15 minus 6 over 3. And whenever you take this, 15 minus 6 is 9. 9 divided by 3 is 3 meters per second squared. So that's an example of how to use this particular acceleration equation. So let's look at another example. It says determine the acceleration of a boat that accelerates from 10 to 30 if it accelerates 2 minutes. So you have a time of 2 minutes, which you know that's not going to work. We have to convert 2 minutes to 120 seconds. And we have the initial velocity of 10. We have a final velocity of 30. And we can solve for the acceleration. Acceleration is equal to Vf minus Vi over t, or 30 minus 10 divided by 120. Now if you notice, the acceleration of the boat is going to be a lot smaller than in the previous example, which makes sense. It's really hard to get a boat to accelerate. But you do 30 minus 10, and that's going to be 20, and then 20 divided by 120 ends up being 0.167 meters per second squared.